Okay, so let's begin. आप लोगों ने लास्ट टाइम जो क्लास है वो ली थी ग्रोवर एल्गोरिथम पे जो हमने वो उस वर्कशॉप ली थी. ओके गुड. सो वो जो टॉपिक है वो हमने पहले भी कवर किया हुआ है. क्वांटम कंप्यूटेशन का जो दोनों कोर्स है तो दोनों में उसको किया था. एंड द रीजन फॉर रिवाइजिंग इट is actually this, that the Grover's algorithm is extremely important. Not just because it's provide a quantum speed up for such problem, but also because we will see in the next several weeks that it has applications in many other areas. uh, Quantum amplitude estimation, amplification, even the algorithms in quantum walks, they are sort of similarly structured, and then other algorithms even for simulating Hamiltonian. So you will see that it will invariably come in one form or the other. So इसलिए जो Grover algorithm है, even though it's very simple, but it has a very wide application, and that was simply the reason that we revised it in that workshop. So today, what we will do, that we will do Grover's algorithm again, but now as a quantum simulation problem, just to get another view of how to visualize Grover algorithm. And then in the next several weeks, we will keep on building on this algorithm to introduce many other concepts for practical applications. So this topic is also actually covered in some way in both courses that we studied in spring and summer, but again I'm revising it also to introduce new things that we didn't do in the introductory course, and also because again that Grover algorithm is extremely important for many algorithms that will come later. Okay, so the Grover algorithm if you recall, is essentially this, that you have an access to an oracle which can mark the solutions, that it implements this function f of x, which is 1 if x is your solution, and it is 0 if x is not your solution that you're looking for. So or alternatively, you can also think of it in this form, that x goes to minus x if x is w, and it goes to x if x is not w. So we have access to an oracle, and our job is to find that particularly marked element. The algorithm was like this, that we started, let me use a little bit compressed notation, that we have let's say n qubits initialized to 0, and then with the header merge we go to a superposition state, equal superposition state of all basis states, and then we have access to an oracle, and the oracle's job is essentially to multiply this with minus if s that basis state which is the solution, and keep everything else in the plus state. And usually we do it if we have another ancilia bit prepared, let's say in minus state, and then we can think of a multi-control gate, something like this, that when that particular state comes in, it activates this NOT gate, and we get a minus sign over here. And since the global phase we can assume with anything, so we think of that phase with this part, and we get this output here. So this then becomes some S prime where the element has been marked. And then once we go through the oracle, we implement another part of the algorithm, which is essentially which does this. So this has another Hadamard, a special oracle, and let's say it also has access to this because this is special because this give a minus sign to every basis state except 0. And then we have Hadamard again. And this part, which is referred to as the diffuser, let's say it's some circuit V, this essentially amplifies the amplitude of the marked state. And if you recall the picture, so one picture was this, that we start with the an equal superposition state, and then this one marks this one, and then this part actually flips it back and takes it higher, and these one comes down. And then we repeat this part R times, where R depends on the number of solutions. So for this circuit, we need to know the solution number of solutions beforehand. We'll discuss later how to, actually in the next lecture, to estimate the number of solutions before applying this algorithm, or how to apply this algorithm to work in a situation when you don't know the number of solutions beforehand. And this R is actually proportional to n square root. And then we do, measurement over here, and our marked state gets on the output. So another way of visualizing this search algorithm is to think about the evolution of this, state. Let's say this state, because this is what we are using to repeatedly apply this part on. Evolution of this state under some Hamiltonian, and imagining this a problem as of Hamiltonian simulation, that you put this state in a certain Hamiltonian, and then let's see what that Hamiltonian is going to be, and then we will also see how to implement it in circuit, and we will see its relationship to this such problem. So this will then turn out to be a special case of this more general Hamiltonian simulation problem. So this is, let's say, Hamiltonian simulation. So this is more general than this. Okay, so our goal is to find a Hamiltonian and its impact on this state S, such that this Hamiltonian, let's call it state psi for now. So this is some state psi, and it has some marked solution. Let's say they are X, and some unmarked basis states. So the goal of Hamiltonian is to transform this state to this state. Okay, so this is S. So we want this Hamiltonian to be such that this S goes to an X state, so that when you measure, you get X at the output. And there can be a couple of possible choices but one choice that we are going to work with is this, that if we have a Hamiltonian of this type, we will see that this will amplify the X. Mama, question? So this Hamiltonian, we will see in a short while, can do this job, that it can take us from this state psi to this state X. And let's see how. There's another possible choices, X psi plus psi X, and Imama has this project to implement. She will work out for both of them, but we are going to work in class with this one. Imama, following almost the same procedure, you will be able to work out the impact of the other Hamiltonian as well. Okay, so this is the Hamiltonian, and since this state psi is essentially a superposition of all basis state. I can also write it like this, just as we did for the Groover problem. So let's say I imagine that there is only one solution here. So let's separate that solution and call it X. So out of this, sum, I have taken out the X term outside, and then whatever is left is here. J0 to n minus 1, but J is now not equal to X. And we can, construct a normalized state, let's call it Y, such that if I, multiply with n minus 1 square root here, n minus 1 square root here, this becomes n minus 1 over n square root, 1 over n minus 1 square root, j from 0 to n minus 1, but j not equal to X. Now this is a normalized state because there are, n minus 1 terms here, and I'm dividing with n minus 1 here. So this is not normalized. Let's call it some Y. And this is also orthogonal to this. And you can see because I have removed X from this sum. So since all the basis states are orthogonal with respect to each other, so this sum doesn't contain X. So when this X is, multiplied, taken in a product with this, it's 0. So let's call this something alpha and this thing as beta and this state as Y. So I'm expressing this state psi as a superposition of the solution and whatever is not solution. All right, and these alpha and beta are now defined. Alpha is 1 over n square root, beta is n minus 1 over n square root, and you can see that they do satisfy this condition that alpha square plus beta square is 1. You can check. If you square and add, you will get 1. All right, so now I have a form for psi. So let's put this psi in here and in here, and then you work it out. So if you work it, if you rearrange things, we can see that I can write this Hamiltonian as something like this: 1 plus alpha square, alpha beta, beta square in XY basis. Okay. Or on the other hand, instead of beta square, I can write 1 minus alpha square. So if we separate identity, then I have alpha square minus alpha square, alpha beta, I can take alpha common. And then we have sum of two matrices, beta X and alpha C, where X is 0, 1, 1, 0, and Z is 1 minus 1, 0. So if you multiply these and multiply alpha, you will get this one. So I've expressed our Hamiltonian in terms of X, Z, and identity gate. Okay, and let's now see the impact of Hamiltonian on the state. And when we have to evolve any state to a state after for some time t, the impact can be h bar h t. जी ये कैसे बना है? सो अगर आप इस साई को यहाँ पे पुट करें ना, इनको evaluate करें, तो you will get some terms with xx, some term with xy, some term with yx, some term with yy, right? तो जो xx है और जो yy है वो diagonal term है, जो xy और yx है वो off diagonal terms, ठीक है, in the xy basis. ये essentially it's a two-level system where one level is the solution, but the other is a superposition of all those other states. But this is essentially a two-level system now. Okay, so to find the impact of a Hamiltonian on any state, we have to evolve it under this one. So let's work with h bar 1 unit, and then psi of t is exponential minus iota ht, and h is there, so minus iota t I minus iota t alpha beta x plus alpha z psi 0. And we can see one thing, this is a constant. So this I commutes with this thing. So I can, separate this exponential into two parts. So one term is exponential minus iota t, because this identity, I don't even need to write it. And the other part is minus iota alpha t beta x plus alpha z psi. Now this I'm going to ignore because this is just a global phase. Okay, I can keep writing it all the time, but it's not going to impact the measurement statistics at the end. So let's just forget about it. And this we can expand as a Taylor series identity minus iota alpha t beta x plus alpha z. Then its square. Its square is iota alpha t square beta x plus alpha z square over 2. Then its cube iota alpha t cube 6 beta x plus alpha z cube, but let me write it just square into beta x plus alpha z and so on. Okay, so if you look at this, this is beta x plus alpha z, and if we expand it, this becomes beta square x square plus alpha square z square plus alpha beta zx plus alpha beta xz. So this is that square term. Now x square is identity, z square is identity, alpha square plus beta square is 1. And if we take alpha beta common, zx plus xz. And now you can easily check by this matrix multiplication that zx is equal to minus xz. You can check. So it means their sum is 0, so this goes away. So this is just 1. So it means this term is 1. Similarly, I broke it into two parts because this is 1 and only this part is left, and so on. So it means we can partition this thing into two parts. One that contains beta x plus alpha z terms, so just इसमें है, इसमें नहीं, इसमें है, and so on. And the terms that doesn't have, beta x plus alpha z. So this one, and the next one, and so on. So if I combine this with this is I plus iota alpha t square over 2, and then the next one and so on. This becomes cosine of alpha t. You can check because this is minus alpha square t square over 2, and this is how cosine is like 1 plus minus x square plus x4 and so on. And then if you look at these terms and this term and so on, if I take beta x plus alpha z common, we are left with minus iota alpha t. And if I take minus iota common as well, so this is alpha t cube and so on. So this becomes sine of alpha t. So this Hamiltonian exponential minus iota ht essentially becomes cosine alpha t identity minus iota sine alpha t into beta x plus alpha. So this is what this operator becomes. Now we can now see what is happening. And actually, let's find out what happens to psi. So if I operate this on psi, psi is alpha x plus, beta y. You put it there and you evaluate this thing. if you're interested in the derivations, you can check the notes from the previous course. I'm just going to write results. So this becomes cosine alpha t psi minus iota sine alpha t x. So this is what psi of t becomes. And you can work out by putting alpha x plus beta y here and evaluating these, operators, you'll be able to find it this one. Okay, now this, if you visualize it in the xy plane, क्योंकि ये जो psi है ना, इसकी जगह पे आप रख देंगे अल्फा x प्लस बीटा y. So you can work out that the y part cancels out and you're left with this part. Did he apply होता है? x सॉरी क्या है? y जो कॉम्बिनेशन है. x सिंगल बिट है. नहीं, ये तो ऑपरेटर नहीं, ये तो स्टेट है ना. ये सिंगल क्यूबिट है और ये सिंगल क्यूबिट ऑपरेटर है. ये भी सिंगल क्यूबिट ऑपरेटर है. क्या 0 1 क्या हो सकता है? हाँ, मतलब ये जनरल स्टेट है ना. हमने it's actually little bit more than two level system, but you can still imagine it like this. You can work it out like this if you want. This is the thing that we want to find out. On psi, and this becomes this beta x plus alpha z is this beta x plus alpha z is Hamiltonian minus identity divided by alpha. And this Hamiltonian was x अब ये जब psi आइडेंटिटी के साथ आएगा तो this becomes psi. जब यहाँ पे आएगा तो this will become psi psi 1. So this plus psi will cancel with minus psi, and this x into psi is nothing but alpha, right? Alpha square or alpha. Yes, alpha, because x and psi psi has alpha amplitude along x. So this becomes alpha and over alpha. So I'm left with x only. So this is just x. Okay. All right. So let's get back here. So I was just going to show that what is happening. So we can see that the Hamiltonian is doing what we initially expected of it. And if you imagine, let's say this is y-axis and this is x, and a space spanned by these two orthogonal states, x, y. So this initial state psi was somewhere here because it had a component alpha along x and a component beta along y. And if you recall, alpha was 1 over n square root and beta was n minus 1 over n. So beta was close to like 1. So that's why it's mostly along y, but a little bit along x. Anyway, but after as time t increases from 0, it is rotating towards x, because as t increases, this begins to increase from 0 to higher term, and this, when t increases, this angle increases from 0, this cosine starts decreasing from 1 below. So this state psi continuously rotates towards the state that you want to reach. So this is the impact of this Hamiltonian that we have figured out. So it means if I take my simulation time t to be, when this will be 0, this will be 0 when alpha t is pi by 2. So when alpha t is pi by 2, my t should be pi over 2 alpha. And alpha was 1 over n square root. So if you take it over there, so this is pi n square root over 2. So if we simulate our state psi, and the initial state psi is very easy to prepare. All you have to do is just apply Hadamard on each qubit, because this is a equal superposition state. So for this, quantum search algorithm, all we need is to simulate under a Hamiltonian H that we initially decided used, and then by applying the Hamiltonian for this time t, for this time, we should be able to reach the solution state exactly, right? There's no problem because I can take this t to be exactly equal to this, so I can reach here. And this is actually sort of a little bit more general from the Grover algorithm. And we will drive that later on. So the next question now is how to simulate our, how to evolve our state under the Hamiltonian. And we will use the same method that we discussed last time, and which is this, that we are lucky already that our Hamiltonian can be written as sum of two terms. So our Hamiltonian simulation, and the method is still the same, that in we can simulate it for this much of time by simulating it for small time delta t and doing it, let's say, some r times such that r delta t is equal to p. So what we have to do is apply this operator r times such that r delta t is equal to p. Then we will be able to evolve our state for this much of time. So all we now have to do is to think about evolving for this time delta t, because the rest is just the repetition. And let's see how we can do that. Exponential minus iota h. बिलाल आपको समझ आ रही है?
Yes sir, आ रही है. लेकिन सर
अच्छा,
थोड़ा सा एक रिक्वेस्ट है कि थोड़ी देर बाद देखिए मिड लेक्चर में थोड़ा सा पीछे से ओवरव्यू दे सकते हैं, क्योंकि आई थिंक थिंग्स आर गोइंग अ बिट टू फास्ट और पता नहीं लगता है कहां से हम कहां पे निकल आए एकदम से. अभी तक तो वैसे ठीक है, लेकिन मिड लेक्चर में थोड़ा सा ओवरव्यू दे देते हैं.
चलिए आप पूछिए करें. मैं काफी चीजें पिछले कोर्स से रिवाइज कर रहा हूँ, बट स्टिल आई एम स्किपिंग लिटिल बिट, small derivations that I think that even if you don't know how to do it, अगर जो हमने पिछले कोर्स में की है, but you should still be able to follow the lecture in this course. For example, जैसे I try to skip little bit of derivation, but then I did it on the other board.
डेरिवेशंस ठीक है, ये होता है ना कि फ्लो जो चल रहा है लेक्चर का, कि हम कौन सी चीज कर रहे हैं वो एकदम से हम स्किप करके, यानी कि हम काफी तेज जा रहे हैं और एक चीज पर दूसरी चीज एकदम से आ जाती है, तो थोड़ा सा ट्रैक वो पीछे से निकल जाता है कि कहां से शुरू किया था और अब जा कहां पे रहे हैं.
चलें, ठीक ठीक है. Okay, so now I'm coming down to this, that we have to find a way to simulate it. And since this h is sum of two terms, the first thing that comes to our mind, that let me call it some h1 plus h2 delta t, that I can approximate it using the initial, what we discussed when we were studying the simulation, Hamiltonian simulation, that since this Hamiltonian H has sum of two terms, so since in general these may not commute, and they don't commute, actually you can check, so I can approximate it for small time delta t with this thing. And now I have to figure out how to implement this one, and let's discuss that. So the first thing that we need to work out is the simulation of this part, and let's see how I can expand it. So using the Taylor series, this can be written as I minus iota delta t xx, then square. The square would be minus square plus but iota square minus delta t square. Actually, let me just write it, iota delta t square. And then the square of this term. Its square is actually itself, because when I write it twice, this x into x is 1, so I get again x into x. Similarly, its cube will be this, its 4 power is this, and so on. So this is just x, and then cube, again x, and so on. Which means that if I take this xx common from all of these terms, I get minus iota delta t square, and so on, which is the Taylor series of exponential minus iota delta t minus 1, right? Because only 1 is missing. If I just take xx common, other than 1, it has all the terms for the Taylor series of exponential minus iota delta t. ठीक है बिलाल?
Yes, sir. ठीक है.
Okay, so to implement this, I now need a circuit that does this. And now, actually, let me make it even easier for you to think about the circuit. Now, our input state psi is a linear combination of x and y. And let's see what it should do to x, this part. So if input comes out as x, what the output should be? Output should be, let's apply x over here. So if I apply x, then x into x is 1, and x into y is x, and this is exponential minus iota delta t minus 1, so into x. So this minus 1 x cancels with this one, and I'm left with exponential minus iota delta t x. So our circuit should be such that if the state input is x, it should multiply it with this phase term. And if input is y, let's see what it should do. If y comes here, then x into y is 0. So all of this goes away, and I into y is y. So output should be y again. So the circuit to implement this part of Hamiltonian is such that it shouldn't do anything to y, but to x, it should multiply with the phase term. And this x is, by the way, is the solution. So it means you can see one thing easily, that I need a circuit that calls the oracle as well, because only oracle know that which of the basis state is the solution. So it means the implementation of this circuit can be done like this. So psi is coming from somewhere here, and I have an oracle that have input on this bus, and then there is this state which is initialized to 0, because this is a part which the oracle, if the input comes here as x, the oracle is going to make it 1. And if the input comes here is not the solution, oracle is not going to do anything to this one. So it means if I have over here a phase gate like this, 1, 0, 0 exponential minus iota delta t, and then this comes here, and then I call the oracle again to uncompute. So I get output over here. We can easily see that this circuit does this job, and you can check. Let's say the input here is y. If it is y here, this control is not going to be activated, right? Because none of the state in y is a solution. So this 0 will remain 0. And this gate, this is a phase gate. This doesn't do anything to 0. 0 goes to 0, and only 1 state goes to exponential minus iota delta t. So since this 0 goes to 0, this does nothing. And then this again, or the y state is coming right here, nothing happens, 0 is 0, and you get the y state at the output. Let's see what happens if input is x. If input is x, this control is activated by the oracle. The 0 becomes 1. And since this is 1, the 1 is multiplied with this phase factor exponential minus iota delta t. So here I have 1 exponential minus iota delta t. And then I call the oracle again to flip my 1 back to 0. And my input is minus iota delta t. And this x, which was coming here, is coming here again. So it means I can think of this phase with this one, because over here the state is n bit x state into 1 bit 0, and over here the state is exponential minus iota delta t, n bit x state into 0. So this circuit has done what this should have been doing. All right, so let's see the second term in our Hamiltonian. So by the same logic, you can easily check that exponential minus iota delta t h2 is identity minus plus minus iota delta t minus 1 into psi. Because psi is also normalized state. So when you will open its Taylor series, the square term will again be psi psi, and cube term again psi psi, and so on. You can do exactly the same thing. So this is what it should be doing. Let's see what happens to input x. If input is x, what it does to it? It gives output as, so I multiply with x here. So x into I is x, and psi into x is alpha. Alpha exponential minus iota delta t minus 1 into psi. And if input is y, if it is y here, then the output should have been y plus beta exponential minus iota alpha delta t minus 1, like this. So this is the difference. So we need a circuit that does this. It, input plus alpha times this phase factor into the same state. And similarly here. Okay, one thing you can see that this part is independent of x, because it has only to do something with the whole state psi and not the individual part. So our implementation of this part will not have to call the oracle. And let me give you the circuit, and then we can see why it does this job. So the circuit for this part is, so the input coming here, Hadamard, 0 coming here, and then control with all zeros, and then the same phase gate, and then uncompute, and then Hadamard here, and that's it. It's a little bit non-trivial actually to easily see that this circuit really does what we are saying that it does. So let's start, analyzing it one by one. So for case 1, when input is delta x. So this state over here is x 0, Then over here, the input is 1 over n square root, some j going from 0 to n minus 1, j 0, right? Because this is header mod, so this x, oops, this is, I need minus 1 power x dot j, j 0, right? Because this is not a zero state, this is a general x state. And this, I hope you imagine that this is something like 0000 plus 0001 plus 0010, but this plus that I'm saying, actually the sign is given by this. Some terms have minus sign, some terms have positive sign, depending on this, phase part. However, you can see that I can separate it into two parts. One part that is just the first term. The first term is for J0. When this J is 0, this is 0, 0, 0, 0. And this last bit is 0. And then whatever is left. Whatever is left is this 1 over n square root. J going from 1 to n minus 1 power x dot j, j into 0. So I separated out the first term because what is coming after this is only impacting this term. When this state is in 0 state, this control is activated and this 0 goes to 1. Okay, Subhan? So this 0 goes to 1. And when this goes to 1, I get this phase factor exponential minus iota delta. So over here, this is 1, everything else the same. Over here, this is 1, and there's exponential minus iota delta t here. And then when you pass through this uncompute step, that whatever I did here, I'm reversing it over here. So this 1 becomes 0 again. And just at this point, my state is 1 over n square root exponential minus iota delta t, 0, 0. बिलाल समझ आ रही है आपको?
Yes, sir, आ रही है.
Perfect. Like this. Okay. Now I still have to do the header mod, but before I do, let me do one trick, because I'm going to do header mod just a little bit later, and I could reverse this header mod if my sum would have been starting from 0. क्यों? क्योंकि ये देखें ना, x का जब हेडर मार लिया था तो सम था 0 से n minus 1 तक, और ये था ज़ाहिर, अगर इस पे दोबारा हेडर मार लगाए तो आई शुड गेट x बैक, क्योंकि हेडर मार स्क्वायर इज आइडेंटिटी. लेकिन ये जो सम है इसमें बाकी तो सब कुछ वही है, लेकिन पहली टर्म मिसिंग है. So what I can do, I can actually add that term here and subtract from this overall thing. So if I add and subtract, it becomes, और ये जो last वाला 0 है, let's just forget, because we are going to be concerned with this thing. Header mod भी सिर्फ इन्हीं पर है. So let's forget this last 0. और यहाँ पे let me add 1 over n square root 0 term in this sum, और इसमें से subtract कर लेता हूँ. So when I subtract it from this, I get exponential minus iota delta t minus 1 into 0 state. So this is the n qubit 0 plus 1 over n square root sum over j0 to n minus 1, now minus 1 power x dot j j. अब जो है वो इसके हम हेडर मार्क लगाते हैं. इस पे जब हेडर मार्क लगेगा तो आई विल हैव 1 over n square root exponential minus iota delta t minus 1. हेडर मार्क ऑफ दिस, इसका हेडर मार्क होता है 1 over n square root sum k going from 0 to n minus 1 sum over k, और इसका हेडर मार्क आ जाएगा just x, राइट? और ये देख लें, ये वही है जो हमें चाहिए. क्यों? क्योंकि दिस इज स्टेट psi अगेन. Psi was equal superposition of everything, and this is alpha, and this is x. So this is what our circuit should have been doing to the x input. So it means this does the job for x. अब similarly अब y input के लिए भी you can work out. I'm going to leave it for you to do that it does the same that we said that it should be doing. I think like ये सर्किट उसमें गिवन है जो नेल्सन चुआंग की बुक में. आई डोंट नो कि उन्होंने खुद से ये डिजाइन किया है or they have taken it from somewhere else. But it seems little bit non-trivial. Okay. नहीं देखें, अगर आप ये सवाल कर रहे हैं कि आप कोई ऐसा काम करना चाहते हैं जो आपने पहले कभी नहीं किया, you haven't seen the circuit, so how you come up with that circuit. So this is actually a really non-trivial question. It's not an easy job. That's why there are not many quantum algorithms to begin with. और उसका जो तरीका है वो वही है जो कि क्लासिकल कंप्यूटेशन का है. आप देखें, हम पैदा होने से लेके 25-30 साल की उम्र जब तक हम कॉलेज यूनिवर्सिटी में आते हैं, we do this classical programming right from our birth. ठीक है, sequentially है ना कि अब you have set of instruction, so you have so much experience कि जब आपको कहा जाता है जी कि एक अलजेब्रा का ये इस तरह का प्रॉब्लम सॉल्व करें तो क्या एल्गोरिथम होगा, you simply say okay, do this, do that and you'll come up. So it all depends on the practice. So the same thing is here. जब आप कोई 150 क्वांटम एल्गोरिथम एनालाइज कर चुके होंगे, उसमें आप देख रहे हैं certain things are coming again and again, then your intuition starts working. Initially आपसे कह रहे हैं कि थोड़ा सा चेंज वाली जो चीज है वो आपको चाहिए, ठीक है. So you can tweak some known circuit later, but ठीक है, and that's how you start coming with new circuit. कोई भी यूं तो नहीं होता कि एक बंदा आज जो है वो क्वांटम कंप्यूटिंग शुरू करता है और एकदम उसको कहते हैं तो वो कहता है अच्छा इसका ये सर्किट होगा, और उसके लिए कोई मैजिक ट्रिक भी नहीं है जी के, या कोई वो तरीका भी नहीं है कि इसके लिए ये होगा इसके लिए ये होगा. देयर इज नथिंग लाइक दैट. सो डिक्शनरी वही है जो क्वांटम एल्गोरिथम लोगों ने डेवलप किए हुए हैं. दैट्स द स्टार्टिंग पॉइंट. आप उनको समझते हैं, यू एनालाइज देम एंड देन यू स्टार्ट डेवलपिंग दैट इंट्यूशन. जो ग्रोवर वाला है, सबसे पहले देखिए इट स्टार्टेड वेरी इजी. सबसे पहला सर्किट था मेरे ख्याल में जो डाइस का सिंगल क्यूबिट एल्गोरिथम था, वो था which really said ke we can do something faster than the classical part. And then Joza extrapolated it to multi-qubit, and they had a slightly more complicated system, but still very simple. You have Hadamard, some oracle call and Hadamard, and that's it. नहीं ये जो डाइस जो आई थिंक 1992 में था. नहीं वो imagine the imagination started in 1980s, like 2-3 people actually. जो इसकी history है ना, it's very fascinating that how people came up with this thing. So the question started, अगर आप शुरू से जाना चाहते हैं तो actually goes all the way back to जिसको कहते हैं Maxwell's daemon, कि जी वो अगर वो है which can close and open the doors, कि कुछ पार्टिकल को जाने दे कुछ को ना जाने दे, so you can go against the statistical principle of balance. So why it's happening? So people started realizing about the connection of information with entropy and these things. And then in 1950s there were these very important questions कि आपने क्वांटम कंप्यूटर खरीदा है जो कि शुरू में ट्यूब्स पे, जो क्लासिकल कंप्यूटर ट्यूब्स से बनता था, ठीक है. यू हैव दोस डायोड ट्यूब्स एंड ट्रायोड्स एटसेट्रा, जिनको बहुत सारी एनर्जी चाहिए. लाइक इट्स फेमस के जो बड़े कंप्यूटर इन सिटीज में होते थे, यू हैव टू शट डाउन द होल सिटीज पावर सप्लाई टू गेट देम स्टार्टेड. सो एक बड़ा लेजिटिमेट क्वेश्चन था कि हाउ मच पावर यू एक्चुअली नीड टू डू अ सर्टेन कंप्यूटेशन, और वो पावर जाती कहाँ पे है, वो क्यों कितनी पावर चाहिए. और लाइक सेवरल आई थिंक 2 to 3 डेकेड्स में इस प्रॉब्लम को सॉल्व किया गया कि एक्चुअली you don't need any power to do the computation. You really need power consumption when you have to erase some information. If you don't erase any information, you don't need to consume power. So essentially, अगर आपके पास let's say 4-bit number है and you want to do something on it, and at the end you still have a 4-bit number. So अब लेट्स से वो जो इनिशियल नंबर था वो उसकी चारों बिट्स जो हैं वो 111 थी और आउटपुट की चारों बिट 000 है। इसका मतलब वट एवर यू डिड, आपने कितने एंड गेट लगाए, उस पर जरबें तकसीमें की, at the end you have erased 4 bits of information. So it means you only need 4 times kbt energy essentially. लेकिन जो नॉर्मल जो क्लासिकल कंप्यूटेशन मॉडल था वो ये है, ठीक है, that you go from multi inputs to one or two or fewer inputs. So बहुत सारे सर्किट्स ऐसे हैं। इसका मतलब है अगर आपका सर्किट जो है वो ऐसा है which destroys many bits of information, you're consuming a lot of energy. So then people came up with this idea of reversible computation, Toffoli and a couple of other people, but mainly Toffoli, I think. कि अगर आप बजाय ये irreversible computation के you start working with gates that have the same number of input and output, then you don't have to erase a lot of information. So your energy consumption in principle should be reduced. ठीक है? But then people even went beyond this, that why instead of having any reversible gates, why not have conservative gates work by preserving the number of ones in the input and the output. So you prepare maps that let's say input पे state है 0011, तो output पे वो combination को different होगा 1010 something, but number of ones here and here they are same. So you're not essentially even destroying any bit of information. So all your circuit is doing basically at the end is just shifting maybe this 10, this one goes to this one, this 0 goes to this. So essentially this shifting happening, so no energy loss. अब जब ये towards the end of 70s, this conservative logic and reversible computation, they were then कुछ लोग जैसे मैनन और ये जो लोग थे कुछ ये उस लाइन से आ रहे थे, एंड देन फाइनमैन एंड कपल ऑफ अदर पीपल दे स्टार्टेड बल्कि प्रॉब्लम तो काफी देर से था कि क्वांटम सिस्टम को कैसे सिमुलेट किया जाए, और they thought the classical computer need exponentially many number of bits. So I think 2-3 people, एक डाइस का कंप्यूटिंग मॉडल था, देन फाइनमैन, मैनन, इन लोगों ने प्रपोज किया कि वी शुड हैव कंप्यूटर बिल्ट ऑन quantum principle. But these were a couple of mad people's thoughts. Everybody's working on other computations. But then in 90s, जो है क्योंकि उस 80s में ये तो पता चल गया कि जो क्वांटम सिस्टम की सिमुलेशन है, you can do it faster on this quantum computer. But that's it. But then in 92 and then 94 and 96, couple of people came up with some problems that they thought that can be solved faster on a quantum computer, and they are not quantum system simulation. As a Dice-Souza problem hai, Bunstein, Wazirani, and then later Simon's problem, they are simple algebra or some computational problem. तो उससे जो लोगों का इंटरेस्ट है इसमें बढ़ना शुरू हुआ, एंड देन इन 96 जो शोर्ट्स का एल्गोरिदम था उसने इंटरेस्ट और जो है वो लोगों का इसमें बढ़ा दिया कि दे आर एंड देन towards the late 90s, many people started coming up with algorithm which can solve, classical computational problem faster on quantum computer than on classical computer. और उस parallel में then there was something else happening in terms of communication, that how you can have secure communication, how the protocol can be broken and so on. So वो जो चीजें हैं then in early 2000s they started converging on sort of in principle agreement among most people that quantum computers, if they can be built, they're going to be very useful. Or फिर labs में people started experimenting. Initially there's a lot of enthusiasm about NMR based computing and photon based computing, but in 2010s and later on superconducting computers. So ज़ाहिर है उतनी देर में Google, IBM, these are big companies with a lot of money, and they started investing. So this is how the things are going. और उसी पैरेलल में जब चीजें जमा होनी शुरू होती गई, तो one idea led leads to another and so on, and we now have a host of quantum circuits. लेकिन मेरे जाती ख्याल में आई थिंक जो ग्रोवर है उसका आइडिया जो है वो बहुत इंजीनियस था उसका, क्योंकि it seems to be of a completely different type of quantum algorithms, that are not Fourier transform or period finding based. But then we will see that lot of other algorithms, they can be, thought of in these terms. So इसीलिए मैं जो ये चीज develop कर रहा हूँ, ये इसलिए कर रहा हूँ कि these ये जो modular है, especially two types of Hamiltonian terms जिनको आप repeatedly apply कर रहे हैं, you can solve a problem. This is going to be useful in many other problems as well. All right, so let's come back here. जी जी.
ये एक चीज नहीं समझ आती कि जब क्वांटम कंप्यूटर्स बने भी नहीं थे और मतलब उनका कोई मैप भी नहीं था, तो why would like a scientist sit down and work out algorithms? मतलब it doesn't make any sense.
So बिलाल फनान का क्वेश्चन है कि जब क्वांटम कंप्यूटर बने भी नहीं थे, तो why do people sit down and start working in an algorithm that will lead to so ये वो question है, why do people several thousand years ago started worrying about why are we here, what is earth and what is universe, and there are animals and there are us, and I think a lot of things are driven by curiosity and not just immediate application. And
Yes, sir.
and sometimes I think intelligent people, and not only intelligent people, I would say that anybody human race पे, at least that's why person theory के लोगों के पास जो भी चीज वो समझते हैं, they are different or unique or better than other people, they try to show it or prove it in certain way. ठीक है? You always see these bodybuilder type people, they're wearing these t-shirts, tight t-shirts and roaming around. Why doesn't a person like me wear a tight t-shirt? So everybody tries to show whatever they got. And I think part of the reason that we have a lot of this scientific progress, that intelligent people, they also wanted to prove something that they have certain thing that nobody else is better than them in that space, and that leads to a lot of speculation and progress in this way. Essentially, I mean, otherwise, वो फनान का question है कि there is no quantum computer and there is nobody even know about a quantum computer. कुछ लोगों ने idea पेश किया and somebody is sitting here and working on an algorithm that can solve a problem faster on a quantum computer. So why? I mean, this is a legitimate question. So, I mean, you would imagine, for example, Peter Shore would be very famous and had a lot of money and would be living a very lavish life. And he might have this much money to do this, but if you listen to him on a talk, he has beard growing this way or part this way, and somebody who's maybe just coming out of a homeless place from a street. So people have different types of motivation, and I think it's hard to pinpoint. हर बंदे की अपनी अपनी theory हो सकती है कि why people do this. यानी फॉर एग्जाम्पल आपको शायद आप लोग भी इधर ही होंगे. Couple of years ago there was Abdul Salam talk by Bob Jaffe, और मैं हैरान था कि उसने टॉपिक क्या चूज किया. उसने टॉपिक बेसिकली उसका ये था कि ये इंसानों का कद 6 फीट ही क्यों है, या हमारा जो लाइफ स्पैन है एनिमल्स का अर्थ पे वो ऑन द ऑर्डर ऑफ 10 20 30 100 इयर्स के करीब ही है. व्हाई इट्स नॉट फ्यू सेकंड्स और मिलियंस ऑफ इयर्स. एंड ही हैज वेरी गुड रीजंस टू से दैट व्हाई. सो लोग जो हैं when they are free and and they can think, they think. Okay, so अच्छा, इसका जो एक पार्ट है I'm skipping के if the input is y, you can show that it does what we want it to do. Ultimately, now we have a circuit like this, that we have something that simulates for h1t and something delta t simulate minus h2t, and then this happens r times, and our state goes from this equal superposition state to a state that we want at the output. And this is actually a very powerful idea, not just for searching, but also if you imagine this S state was something like this. What we have done, we have amplified this amplitude and reduced this amplitude. Of course, since this is a sort of equivalent to two orthogonal states, so if this goes up, this has to go down for normalization. And this is called amplitude amplification. And this basic idea of thinking about a quantum problem in this sense that we start from a certain state, and 99% of the time what I have seen is that initial state is actually equal to superposition state. So that's why most circuit actually start with the Hadamard transform, because you then group everything there, because your solution is one or more of those states that are inside S. And then your job essentially is to come up with an amplitude amplification scheme, or which you have a certain criteria to for those S states to be for the states to be amplified, and then you do it a bunch of times. Then at the end, your output is some amplitudes are amplified and some amplitudes are reduced, and that's how your algorithm should work, and that's how actually most algorithms work. And that's why we will also see that many algorithms that we will study from this point on, they would actually look a lot like this. Many algorithms. So that's why this Grover search algorithm is, sort of an important thing. ये जो H1, H2 है, मुख्तलिफ algorithm में वो change हो जाएगा. इसमें किसी में कुछ और हो सकता है. But the basic form is going to be like this. All right. So there's one question which is left to be answered. What this delta t should be. ठीक है. अब हमने लास्ट टाइम, क्योंकि ये डेल्टा टी की जो चॉइस है, इट विल इंपैक्ट आर. आप जितना डेल्टा टी छोटा लेंगे आपका आर उतना बढ़ जाएगा. लेकिन हमने लास्ट टाइम ये पढ़ा था कि अगर आप किसी ऑपरेटर को अप्रोक्सीमेट करते हैं इस तरह से, then there is an error which is of the order of delta t square. So if I reduce my delta t, my error will go up. My error will go down, but my R will go up. But if I increase this, R will go down, but error will go up. But remember, this is a general case. For this special case, actually, I haven't worked out, but my guess is that this error is actually independent of delta t. Or at least, error is a function of delta t, which is not just, this sort of direct dependence. Small delta t would mean higher delta t. But this is something that Imama will have to work out by including the terms in this Hamiltonian that we left out. So we approximated this with this, but then the terms that we have left out, we should, work out what's the impact of that. Because my guess is that I just computed it for the first term, delta t square, and actually its expectation value was 0. It means that the impact of delta t is constant. It's independent of delta t. But then there were terms delta t cube and so on. I didn't do it. You should probably check them or maybe combine all of them together. And my guess is that for these particular choices of A and B, the error is either independent of delta t or it's a periodic function sort of delta t. Anyway, so there's another way of checking the value of this delta t, that what we should use, and that is, let's try this delta t operator in another way. If we have this operator written like this, and now these are calculations that I'm going to skip, which are a little bit tedious, but they can be done. That this can be expressed as like this. I minus 2i sine delta t by 2 cos delta t by 2 psi plus z by 2 plus sine delta t by 2 psi cross dot r, where this r is x hat, y hat, z hat, and this psi bar is 2 alpha beta 0, this and this z hat is 0 0 1. Anyway, so but if you compare it with the general rotation matrix, because in a two-level system, each unitary gate is essentially a rotation around an axis, and that axis is given by the cosines nx and y and z. So if we compare this, we see that the axis is given by this part. This is the axis. So this is psi plus z part. This is psi cross z. So this is rotation axis nx and y and z, and the angle by which an operator rotates is given by this. If I put this one equal to cosine theta by 2. So if we put this cosine theta by 2 equal to this can be rewritten in this form. So it means each application of this operator u, if I go to a block sphere, which is, which has one axis representing x state and the downward state is y, just like this is 0 and 1. So this is a two-level system. So let's say this is my x-axis, this is y-axis, this is z-axis, and this is x state and this is y state. So any operation u is essentially a rotation on this block sphere around a certain axis, and the axis is given by this. So this is my axis. So, and if you recall, the state psi was a linear combination of x and y, where alpha beta were real numbers. So the state psi is going to be somewhere here. Okay, because if this alpha is 0 and beta is 1, my state psi is this, exactly downward. If beta is 0 and alpha is 1, my state is exactly up. But if, let's say, alpha beta are equal, my state is exactly along x-axis. But since when we started, this beta was large, n minus 1 over n. So my state is in this plane, if this xz plane is somewhere over here. So this is my starting plane. And there is this some axis r. And when I apply u to this actually rotates around this axis by some angle theta given by this. And when we rotate it by r times and keep rotating, so this psi keeps going like this, gets this, and finally it goes along my solution axis. Now, to decrease the value of r, I should maximize this theta. And we can see the maximum value of theta is going to be when this is minimum, because theta by 2, cos theta by 2, when it is 0, my theta by 2 is either, pi by 2. So this is minimum when this is maximum. And this will be maximum when my delta t by 2 is pi by 2. So or when delta t is pi. So this means that I should choose delta t to be pi. When delta t is pi, this is pi by 2, which is 1. So cos theta by 2 is 1 minus 2 over n. So this is a maximum possible rotation that we can get. That's why, there was a possibility, जब आपको बताया कि जी, we can simulate with the t, we could have, chosen delta t exactly equal to that t. But this is the maximum delta t that we can choose, because after this essentially the rotation starts to decrease, because when delta t increases from this again starts to increase and my angle starts to decrease. So if we choose this delta t pi, and I can compute this theta actually turns out to be 4 over n square root, because this theta is close to pi by 2, so I can uh, I can actually write it. I want to find an analytical result for theta. So I can just take cos inverse because, of course, theta is that, but I want to find an analytical result. So this theta by 2 is close to pi by 2. So let's write it in certain way that I can use some approximation. Because if this theta would have been close to 0, I could have written it 1 minus theta square. But I can't do that right now. So one way to do is that let me see how I did this. I think I took a square on both sides, so this becomes cosine square theta by 2, 1 minus 2 over n square, and then I can write this I have computed it to be 4 over n square root. Okay, so let's try to approximate it. So for this is close to pi by 2. So let me write it as some alpha as pi by 2, let's say minus theta by 2. So since this is close to pi by 2, when it means alpha is small, so we can expand cos pi by 2 minus theta by 2. So this is cos pi by 2, cos theta by 2, cos pi by 2 is 0, and minus plus, so sine pi by 2, sine theta by 2. So this is sine theta by 2. Now let me, so this means that theta by 2 is alpha pi by 2 minus alpha. So let's write it in terms of alpha. So this is pi by 2 minus alpha. So if we expand it, this becomes cos pi by 2 cos alpha minus sine pi by 2 sine alpha plus. So this is sine alpha. So this alpha is small. So I can write this as sine alpha. So this becomes sine alpha as 1 minus 2 over n, which means that alpha is approximately 1 minus 2 over n. And since alpha is this, pi by 2 minus theta by 2, from here, theta is, I don't know, you can compute theta from here, because I actually want to compute r from here as well. So this is the amount of rotation that we get in one application of u, and I can compute this total angle that I have to go all the way from here to here, because I know what alpha, because the psi has a projection alpha along this x-axis, this axis. So alpha is 1 over n square root. So from there, we can compute this total angle. And if you divide total angle by this angle, which is rotating after one application, you can compute this r, and it checks out with the r that we computed earlier when we were discussing the rotation. Did we? नहीं, हमने किया तो नहीं था, वो तो जस्ट देखा था कि अगर उसको उतने के लिए करें तो we can reach there. So it means that Hamiltonian is doing the thing that we think it should be doing. क्योंकि उसका सर्किट तो बनाना ना, वो तो जस्ट हमने देखा कि हम हैमिल्टनियन को अप्लाई करें टोटल हैमिल्टोनियन को, ठीक है। तो ये काम करता है। तो अब नेक्स्ट काम है कि उस हैमिल्टोनियन को सर्किट में इंप्लीमेंट कैसे करें, ठीक है। सो इंप्लीमेंट करने के लिए हमें पता है कि हैमिल्टोनियन इज सम ऑफ टू टर्म्स, ठीक है। एंड वी कैन दैट टी वाज वेरी लार्ज, सो we divided the simulation time t to small intervals of delta t times, और फिर हर डेल्टा टी में हमें देखा कि h की दो टर्म्स हैं, तो दोनों टर्म के लिए एक एक सर्किट होना चाहिए, ठीक है। सो ये आगे जो है वो प्रैक्टिकल पार्ट है, वहां तक तो हमने जस्ट ये देखा कि ओके द प्रॉब्लम कैन बी सॉल्व दिस वे, ठीक है। तो जब इसको इंप्लीमेंट करना है आपने उसमें किस किट पे, लेट्स से, तो दिस इज व्हाट वी हैव टू डू, और इसका भी सर्किट आपको दे दिया, इसका भी दे दिया, ठीक है। वी डू इट ऑल टाइम। सो आर हमने निकाली, इट्स यू नो ऑफ द ऑर्डर ऑफ एन स्क्वायर रूट, ठीक है। और वो क्योंकि हमने डेल्टा टी पाए रखा था ना, हाँ ये है ना डेल्टा टी, तो अब यहां से आर जो है वो आप निकाल सकते हैं। सो आर है टी बाय डेल्टा टी, और टी कितना था, टी था पाई ओवर यहाँ पे वो टी रखे तो आपका वो आर वही आ जाएगा, ऑर्डर ऑफ एन स्क्वायर रूट, ठीक है। सो जिस तरह उसमें हम कंप्यूट करते हैं ना, सो उस आर से उतनी टाइम जो है वो आपने करना है। अच्छा अब लास्ट चीज, व्हेन यू टेक दिस डेल्टा टी पाई, सो व्हाट हैपेंस, जब डेल्टा टी पाई है तो ये क्या बनता है, जब डेल्टा टी पाई दिस बिकम्स 1 0 एक्सपोनेंशियल माइनस आयोटा पाई, तो एक्सपोनेंशियल माइनस आयोटा पाई होता है 1 0 0 cos pi is -1, so this is -1. So ये क्या कर रहा है, ये अब सिर्फ माइनस फेज देगा जब यहां से x आएगा, so जहां पे ये 1 आएगा, ठीक है। दूसरी तरफ ये देगा प्लस फेज। सो ये एग्जैक्टली वही काम है जो ग्रोवर ने कहा था कि आप एक पार्ट सर्किट का वो बनाएं जो स्वाय 0 0 स्टेट के बाकी सबको माइनस दे दे, या इक्विवेलेंटली इट्स उल्टा भी है कि आप 0 0 स्टेट को -1 दे दे और बाकी सबको प्लस दे दे। तो दिस इज डूइंग एग्जैक्टली द सेम थिंग। और जो दूसरे वाला सर्किट है, जो ये वाला है, ये देखें जब ये भी -1 हो जाएगा, सो 1 0 0 -1, सो इट मीन इट्स गिविंग minus phase when the input is x, and it's giving positive phase when input is y. So this is the Groover oracle to begin with. So Groover ने यही कहा था ना कि एक पार्ट सर्किट का हो जो x को माइनस दे और बाकी को ना दे, मार्क कर दे। और जब डेल्टा टी पाए लेते हैं, और देखें डेल्टा टी पाए जो है वो ऑप्टिमम था हमारा, क्योंकि उससे जो मैक्सिमम रोटेशन हो रही थी। इसका मतलब है ग्रोवर ने बाय चांस जो पहला ही एल्गोरिथम डिस्कवर किया क्वांटम सर्च का, वो खुद ही ऑप्टिमल है। इट्स ऑलरेडी ऑप्टिमल, यू कैन डू बेटर देन ग्रोवर नाउ, बिकॉज इट्स ऑलरेडी फॉर डेल्टा टी इज इक्वल टू पाई। समझ रहे इस बात को कि ग्रोवर का जो एल्गोरिथम है वो यही है, क्योंकि उसमें हमने डेल्टा टी को पाई ले लिया, और डेल्टा टी पाई पे जो एक सिंगल यू की एप्लीकेशन थी उससे जो एंगल मिल रहा है, इट वाज मैक्सिमम पॉसिबल। So that's why Grover's algorithm is actually already optimal in setting up quantum search problem. Okay, so next class we will do quantum amplitude estimation or quantum counting, etc., and we'll start building from there. Thank you.